Welcome. So we have to show that if u of xy and v of xy are harmonic functions in a region R, then the function partial u partial y minus partial v partial x plus I times partial u partial x plus partial v partial y is also an analytic function of z given by x plus I y. So this I'll prove this. Now, since u and v are said to be harmonic, then so since u of xy and v of xy are harmonic, functions in R, therefore we can say partial squared u partial x squared plus partial squared u partial y squared is 0. Let's call this one equation 1. And partial squared v partial x squared plus partial squared v partial y squared is equals to 0. Actually, this is from definition of a harmonic function. Then let capital F of z be given by capital R plus IS be partial u partial y minus partial v partial x plus I partial u partial x plus partial v partial y. Let's call the given expression f, which is the same as R plus IS. Then equating real and imaginary parts, we have R is given by partial u partial y minus partial v partial x, and S is given by partial u partial x plus partial v partial y. So this implies that partial R partial x, differentiating this equation with respect to x will give us partial squared u partial x partial y minus partial squared v partial x squared. Let's call this one equation 3. Also, differentiating this one now with respect to y, so partial s partial y will be partial squared u partial y partial x plus partial squared v partial y squared. Call this one equation 4. Also, if you define partial r partial y, then you'll get partial squared u partial y squared minus partial squared b partial y partial x, and then let's call this one 5, and then partial s partial x will be given by partial squared u partial x squared plus partial squared b partial x partial y. Let's call this one equation 7. So when we put together, putting together, or actually by observation, so from these two given, from these equations, so putting the value of partial squared u partial x squared from equation 1 in equation 6, we have partial s partial x is equals to minus partial squared u partial y squared plus partial squared v partial x partial y. Remember from equation 1, it's the same thing as saying partial squared u partial x squared is negative partial squared u partial y squared. So that's what we are doing here. So there's a negative sign here. And then putting the values, the value, so let's call this one 7. Value of partial squared v partial y squared from equation 2 in equation 5, we have, so equation 5 is the one that has partial, in equation, equation 4, let's say equation 4, we're still using S equation. In equation 4, this equation here will have partial s partial y will be given by, so this is what we are replacing, so partial squared u partial x partial y, then minus partial squared v partial x squared. Call this one 8. Now from the expression, from 3 and 8, so remember 3 was partial r partial x equals to partial squared u partial x partial y minus partial squared v partial x squared. This was what defines equation 3. So from equation 3 and equation 8, you see they are the same equations. it implies partial r partial x is the same as partial s partial y. And then our equation 7 from equation 7, i.e. equation 7 is partial s partial x given by negative partial squared u partial y squared plus partial squared b partial x partial y. This is our equation 7. And question 4 was given by the expression for partial r partial question 5, not equation 4. Question 5, which expresses partial r partial y partial r partial y is given by partial squared u partial y squared then minus partial squared b partial x partial y. It tells you that these two are negatives of each other, implies that partial r partial y is the same as negative partial s partial x. So therefore, the Cauchy-Riemann equations are satisfied and hence the given function is harmonic, is analytic. So when Cauchy-Riemann equations are satisfied, so that they prove that the given function is analytic. So that's how we are supposed to prove that given statement.